In the last revision session, we ran out of time before we could complete a complete example with taking a transfer function for some process and going all the way from constructing the Bode diagram and the Nichols chart and then applying a controller, even a simple one like this. So that's what we'll do in this session. And here's our simple process. So we have no zeros here. We have nothing, no s function in the numerator. In the denominator, we can see s functions. So this is one multiplying factor, s plus 1 over 1,000. And there's a second multiplying factor for s plus 1, and that's squared. So that's the process. And we know we are going to apply a controller and so on eventually. For right now, we'll just start with plotting these diagrams for the process itself. To begin with, when we want to plot the Bode diagram, of course, we'll want to plot the log modulus, and we recall from, I guess, high school that these basic properties apply. So the log of the product of two numbers is the sum of the logs of each of the numbers, and the log of a number raised to a power is the power multiplied by the log of that number. So with those two properties, let's talk about the log modulus for the Bode diagram. So of course the log modulus is defined as 20 log 10 of the modulus or the magnitude of g of I omega. So of course in our controller function, this is generally speaking a function in S, but we are selecting specifically S equals I omega. So in the complex plane, we are selecting the specific line I omega. And to understand why we do that, please review in the previous revision section or session. We covered that in some detail. So we outlined the logic for figuring out encirclement of -1, 0, and we talked about going around the entire right-hand plane, and part of that showed that all we needed to do was use S equals I omega. So be sure that you can follow that logic clearly. That's really the basis of this whole course. So anyway, S equals I omega, we won't review that right here, we'll just use it. So S equals I omega, that's applied here. So we apply it in the function, which then looks like this. And then we just have to start using the properties of logs. So first of all, we can separate these three groups of factors. We can separate them using the product rule here. I guess we can call it the product rule for logs. And of course we split out the 1 over 10 here, and then we split out this term in the denominator, so that's there, but of course this is appearing in the denominator, so we can rethink this factor as being this function raised to the power -1. So if it's a function raised to the power -1, we can bring that -1 out in front and multiply by log of that. So we take the a -1, we read that as this raised to the -1, so it's -20 then times log 10 of that function. So that takes care of that part. And then moving on here, we have the power this time of 2, and of course again that's in the denominator, so we can really view that as this function raised to the power -2. So we can say -2 times that 20 there. So here we've already used the minus, so it's -40, and then log 10 of that function for I omega plus 1. So that's what we have here. And then to find the places where our function is going to turn, we like to write this in the form I omega plus some constant. So when we write it like that, then that constant tells us where the curve is going to turn. So we will, in this one, it's already in I omega plus constant, so we can say it's going to turn at 1 over 1,000. We can leave that as it is. In this one, we've got here 4I omega. So we want to rewrite this as I omega plus some constant. So all we have to do is group out that unwanted factor, that 4, And then to maintain equality, we have to write this 1 as 1 over 4. So 4 times that 1 over 4 gives us back the 1, and then we've grouped out the 4 from there. So you just group out the factor that you want to get rid of, and then you just apply the property of logs. So you can split out the 4 here. So we split off this 4. So 40 log 10 4, we remove that as a factor here, and that leaves us with 40 log 10 I omega plus 1 over 4. Right, so this is the friendlier version for our transfer function in terms of its log modulus. So to draw this line, we first think about what happens when omega is close to 0. So when omega is close to 0, of course, we can just set zeros in here, and that leaves us with minus 20 minus 40 log 10 4. So minus 40 log 10 4. And then here, what's left over is 1 over 1,000 log 10 of that times minus 20, so that's there. And then here, again, we get minus 40 log 10 1 over 4. Right, and by the way, you should recognize that these two are going to cancel, or not cancel, these two will, okay, anyway, you can just work this out as a number, and we'll get a value of 40 if we do that. So when omega is 0, we have an L value of 40. And then as omega increases, and when we reach 1 over 1,000, like we said, the line begins to curve, and then we will get that going down at minus 20 decibels per decade. So here we are talking about this contribution. So we've already said this part plus the omega equals 0 part. So we have that it's starting at 40, and then as omega increases, these terms become more important, and the first contribution we get is from this term. So at 1 over 1,000, the line starts to get a big contribution from this term, and when it's close to 1 over 1,000, and when it starts going past 1 over 1,000, then we start to get that for every factor of 10 here, right? Imagine omega is large enough and larger enough than 1 over 1,000 that we can start to ignore this term. Then for an increase of 10 here, then this is effectively going to be log 10 of 10, which is like a 1. So for a factor change of 10 in omega, we have a change of 1 here, which means that L is going to change by minus 20. Right? In other words, so to summarize that again, for a factor of 10 change in omega, we are going to see L changing by minus 20. So that's what happens at around 1 over 1,000. The line slopes down at minus 20. And so we can say this another way. First, we often call L having units of decibels. And here, when we talk about a factor of 10 for omega, right, 10, remember years, it's a decade. So we can say minus 20 decibels per decade. So L is increasing by minus 20 for every factor of 10 in omega. So minus 20 decibels per decade. So that's what this term starts to contribute as as omega starts increasing around a value of 1 over 1,000. And then as omega starts to increase further and it reaches the grand value of 1 over 4, then this term starts to play a major role as well. So in this case, for a decade in omega, we have an additional minus 40. So we already have a minus 20 contribution here, then we start to get an additional minus 40. So we are expecting to see minus 60. So we'll start to see a minus 60 decibels per decade just after 1 over 4. So that's already enough information to plot out our log modulus part of the Bode diagram. and I'm going to do that here in this paintbrush. There's the line tool, so just sketch the axes. So L versus omega, and we have that it starts out at a value of 40. So we've got starting at 40, and then we are going to reach an omega value of 1 over 1,000. So around 1 over 1,000, it's going to slope down at minus 20 decibels per decade. So we'll draw that here. Let's say that's minus 20 decibels per decade. And then when we reach around 1 over 4, it's going to slope at minus 60 decibels per decade. So let's draw it like that. So let's put in some labels here. Just mark these points. And check. So we are plotting L against omega. So I'm just going to type the name. I don't think I can do the Greek symbols here without a lot of poking around. So here, this is at a value of 40. And then this is a value of 1 over 1,000. And this is a value of 1 over 4. And we've got a slope here of minus 20 decibels per decade, and this is minus 60 decibels per decade. Okay, so that's what we can get just by formulating this expression a little differently and finding some features. And of course we can do this also by running the code, and I'm just going to put that in here. Okay, I have run this. So here you can see for this function we can start. So here I'm actually generating all the values for omega, and we're testing to see if this agrees with the Bode diagram we've drawn. So you can see around 40 we are flatlining, and then at a value of around 1 over 1,000 we find the line is curving here, and we are getting this gradient. And if you look at this, the scale is not so easy to see, but for a factor of 10 here, if you produce these lines back, you can see this is about a difference of 20. So for a factor of 10, we've got a gradient of 20, so that's 20 decibels per decade here. And then at around a 1 over 4, right, 0.25, which is somewhere here, we can see the line is curving again. And down here we are getting, or we are supposed to get minus 60 decibels per decade. So let's take a decade, and then let's look across from these 2 points. So the difference in L here, you can see is about a 60, right? So this looks like minus 60 decibels per decade. This looks like minus 20 decibels per decade. It's intercepting in the right place. It's turning over in the right place as well. So this is a reasonably good way of drawing the log modulus part of the Bode diagram. And of course, that's only half the story. We also need the angle, and to develop the angle, we use this property. So the argument of the product of two complex numbers is simply the sum of the arguments. And we did show, not quite a proof, but we showed why that was true in the revision, in the previous revision session as well. So anyway, we can use this if we are looking for the angle of g of I omega, we can say that's equal to the angle of all those factors, and then we can use this property to split that up. So of course here it's the angle of 1 over 10, and then minus the angle of this function, minus twice the angle of this function. So that's fine. Then this is of course the angle of a real number. So if it's a pure real number and it's a positive real number, then that's pointing along the angle of 0, right? If you imagine the complex plane, well, let's draw it here. So if we've got the complex plane like so, and if we've got a pure real number, right, a pure positive real number, so that's sitting somewhere there, then you can see we would be pointing from the origin to that number. So that's an angle of 0, right? That's if it's a pure imaginary positive number, a positive imaginary number, then that would be an angle of 90. So for a positive real number, that's an angle of 0. So the argument of 1/10 is a 0. And then here, of course, the angle is going to be the arctan of the y part, which is omega, divided by the x part, which is the real part. So the real part is 1/1000. So 1/1/1000 is 1000 times omega. So that's the angle contributed from this term. And then from the other term, of course, in a similar way, we can say that the argument of 4I omega is going to be the arctan of 4 omega over 1. So that's the other contribution there. So if you look at this, it's telling us when omega is 0, of course, this whole thing is 0. And then as omega starts to rise, when we are close to 1/1000, then this is going to be arctan of this number around 1. So the function will cross to around minus 90 degrees. And then as we go past that, we get a further contribution around 1/4. So in this factor, it will be, again, a contribution of minus 90 degrees, but it's 2 times that. So it's a contribution of minus 180 degrees. And then we still have the minus 90 degrees from this term. So minus 90 minus 180. So we'll eventually get minus 270 degrees. So we expect to start from a 0. So I'm just going to draw it on the same axis. So we will start from a 0. We'll start from a 0. And then we expect it's going to curl down to, we'll start from there, and then it's going to curl down to around, okay, I don't want that curvy line, right? So it's going to go down to around minus 90 and then minus 270. And then, of course, it's a continuous line, so it's really a curve that's going. It's going to be something like, isn't there a little pen tool? Yeah. So it's going to do something like that, and then something like that. Okay, and if you go over to the code, when you run that, that's what you find, right? So that's enough detail to plot the argument side of that Bode diagram as well. Okay, so that's the Bode diagram all plotted. And now what we actually want is the Nichols chart. So on the Nichols chart, we have a series of contours which show us the closed loop version of the functions when given the open loop versions. So we just need L open loop and theta open loop. And of course, on our Bode diagrams, we have L open loop and theta open loop. So what we can do is select a series of values in omega. So we could pick omega as 10 to the minus 5 and then ask what's L at 10 to the minus 5, what's theta at 10 to the minus 5. So we can see a point 40 and and 0. So 40 and 0. So we look here, here's 0 for the angle, and 40 is here. And you can see, yes, the curve has started on that point. And then we just pick more values for theta. So if you pick 10 to the minus 4, L is still on 40, 10 to the minus 4. Here we've started to curve down a bit to, let's call that minus 10. So yeah, it's gone in a bit to say minus 10, and we're still on the 40 there. Let's take a value at the end. So here at omega is 1000, you can see this is around minus, call that 240, or 220, minus 220 for L. And here is minus, call that 270. Well, that is 270. So minus 270 and minus 220. So minus 220 and minus 270, there's the point over there. So you just pick points. So along each of these curves, omega is a parameter, right? Each curve is a parameter, or the independent variable there. So if we eliminate these two and instead plot these two curves against each other, then that's in effect the curve that we are plotting here. Now, if you look at this, this series of values, this has gone over quite a range. It's gone from 50 to minus 200. And in fact, the Nichols chart that I'll give you in any test or exam won't have such a large range in L. So I'm just going to reduce the range on the frequencies. It's only because I've used such a large range on my frequencies that it's going so far. So let's just redraw this whole thing for a more limited range in the frequency, and let's try from minus 1 to 1 instead. Rerun that, and I can see, let's reduce the end value here. So let's just try 0. Okay, I actually want to pull this back a bit and stop this one a bit earlier. So I'm going to say minus 1.5 and minus 0.5. So this is the log spaced set of values for omega. Okay, so that's the Nichols chart. So normally in a test or exam, I'll just give you these axes, so all these contours. Remember, these contours are for the closed loop log modulus values and the closed loop theta values. Right, so the blue lines are the thetas, the closed loop values, and the red lines, sorry, the blue lines are the log modulus, and the red lines are the theta, the angle. So those are the closed loop versions of L and theta, and on the Cartesian coordinates here are the open loop values. And we said long ago that a closed loop value of 2 is fairly desirable, and this is found in practice, right? I don't have a rigorous explanation here. Well, there is a semi-rigorous explanation when we if you look at second order underdamped and overdamped, if you look at that analysis, I think that's in notes 03, you can see why LC equals 2 is a good choice when trying to decide on a controller. If you can get your process to exhibit LC equals 2, it's a fairly well-controlled process. So here you can see the process is not sitting on L equals 2, but for a small shift upwards, it is going to, we could make it sit there if we could shift this curve upwards. And of course we can shift the curve upwards because we are talking about using a P controller. So a P controller is in effect going to multiply our process by a constant. And I think I've written a bit about that here. So if we multiply our process, if we implement a P controller, that means we will be multiplying by Kp in our open loop transfer function. And so if you look at what that results in, if you use that property of the logs, that's basically a factor that you would, or a term that you would add to your process term. So we have so far been talking about the process only, Now by adding proportional control, we are basically shifting that curve vertically. Right, you can see Kp is a constant, and we living in the real world can only shift, we can only apply real values for Kp. So this is adding a real number, so it's going to shift that curve vertically. So this term is not going to change the angle, right? It's if you look at this, it's not going to shift us in this direction, it's only going to shift us in that direction. So as we increase Kp, this curve is going to shift upwards. So we can simply choose to increase Kp until the process line becomes a tangent to the 2 decibel line, right? And that's how we choose our constants. And here, if you look at this difference, it's actually a very small difference. This process is already quite close to being well controlled. We could call this distance perhaps a 2. So here I'm saying we just need delta L to increase by an amount of 2. And if you look at the influence of Kp, that's what we wrote. And so we want delta L to be 2. So that means we want this part to equal 2, right? So that's all written there. So we want this part to equal 2. So 20 log 10 Kp equals 2. So we can just solve for Kp then. So Kp, if you take 10 to the power on both sides, so divide first the 20, so delta L over 20, and then 10 to the power that, that's going to be Kp. And if you work this out, you find Kp equals 1.26. So that's the value of Kp that we can apply, and then our process will be sitting right on Lc equals 2, and then we can say that that process is performing fairly well. It means we will see some slight oscillations, but they'll disappear fairly quickly, and also that process is going to respond fairly well. So of course you can create an ultra stable process, right? If you set, for example, fractional values for Kp, then and you shift the curve right down, then that process will be extremely stable, but it's also going to take a very long time to respond. So if you tell that process, okay, now I want a set point of maybe 40 moles per cubic meter in the reactor, then that process was going to slowly and sluggishly respond to that. So by operating closer to this 2 decibel line, yes, the process is getting closer to that -10 point that we don't like, but at the same time it's keeping us reasonably far away from it, that it's going to respond well enough. So that's a good criterion when we say we want reasonably good control. Lc equals 20, that's the line we want to get close to, and with Kp we can shift it. So you can also think about with PI controllers. So in a proportional integral controller, the proportional part will shift it vertically, the integral part is also going to shift it horizontally, and I'll leave that to you as an exercise. Of course, a PID controller, then the derivative part is going to do something else. So you can play around with the code and try out those other controllers and see how the green line moves around for those. Okay, so that's what we can do for answering this question. Let's do something in addition. Let's just talk about drawing the root locus diagram for this. So if you go over here, that's what I'm doing. So let's go back to the original function in S, and if we wanted to plot the root locus diagram for this, we can use the usual rules. You can see here we've got no zeros for this function. We do have, and be careful here, we have 3 poles, right? We've got one pole here. So yeah, S equals -1 over 1,000, that's one pole. And then here we've got 2 repeated poles. So S equals minus 1 over 4. That's going to be the source of 2 new asymptotes. Right, so there are 3 poles and no zeros, and the poles are at minus 1 over 1000 and minus 1 over 4. So we know at least these these loci are starting in the negative real plane, so we have some hope of stability. Let's see how long that lasts. So let's see, no zeros, yeah, okay. So the center of gravity, we said we could find the center of gravity for our asymptotes from this formula. We had also said that if you have any zeros, one or some of your loci will wrap into those zeros. Here we have no zeros, so we don't have to worry about figuring out which thing is going to go into which zero. We have no zeros, so all the asymptotes follow some kind of center of gravity style approach, right? So the center of gravity, we work out the sum of the poles minus the sum of the zeros over n minus m. So the sum of the poles here, and again, we've got the 1 pole here, and we count this as 2 poles. So it's minus 1 over 1000, minus 1 over 4, and then minus 1 over 4 again. Then minus the zeros, there's no zero, so minus 0, and then n minus m. And here it should be, there are 3 poles and 0 zeros, so that's a 3. So let me recalculate this. Minus 1 over 1000, minus 1 over 4, minus 1 over 4, all of this over 3, so minus 1.67, which is minus 1 over 6, right? So anyway, minus, or rather 1 over 60, anyway, minus 0.167. So that's the center of gravity. So we can see on the negative real axis, ignore that comment, 1 over 6. It's not 1 over 6. Just write it as 1 over minus 1,67, right? So that's where that center of gravity lies, and then we need to know the angles of departure around that center of gravity. So here we run k from 0 to n minus m minus 1, which is 3 minus 0 minus 1, which is 2. So the series of k values is 0, 1, and 2. And then if you apply that there, when k is 0, then this is 1 over 3 pi, so pi over 3. And then when k is 1, then that's 2 plus 1 is 3 over 3, which is 1, so that's a pi, so there's your pi. And then when k is a 1, then that, when k is a 2, then that's 4 plus 1 is 5 over 3, so 5/3 pi. So that's an angle of 60 degrees, 180 degrees, and minus 60 degrees. So that's actually enough information. So you can say I've got 3 asymptotes, one originating from minus 1 over 1000. So that one's likely to point, let's see, the leftmost one is there. And then you've got 2 at minus 1 over 4. And then you've also got this center of gravity point, and you've got some angles for that. So let's put that all down. So first, your minus 1 over 1000. So minus 1 over 1000 is going to be right in here. And you can see 2 asymptotes originating here. And then you've got you've got minus 1 over 4. So that's here, right? So minus 0.25. So that's there. So in terms of your angles, you've got this pi. So you've got one shooting off like that. And then from the center of gravity, right, minus 0.167. So that's somewhere around there. and so if you apply the angles 60 degrees there, minus 60 degrees there, so those are the asymptotes that you're going to get. If you look at this process in this way, you can see that it's going to be unstable pretty quickly. Remember, these lines are extending out as we increase the value of k. And here's your 0, so you can imagine a line going here. And so we cross over into positive real number territory around this point. So for kp values that take us onto positive real number territory where things are unstable, for those kp values, the process is unstable. So we actually have a constraint, a very fast upper limit on kp. So we don't want kp values that go beyond that. And in the code, I had plotted the graph that you could look at quickly for that. So here it's plotting as we vary kp, how the real part is changing. And so you can see the real part goes positive for kp values. Maybe that's just 5 or something like that. So so we can use the root locus diagram to quickly analyze for an upper limit for kp. So as much as we've got now these sophisticated Bode diagram ways of plotting things and finding out how we can optimize for good performance, it's always useful to go back to our root locus diagrams, and in a way it's kind of easier to observe for instability and things like that. Okay, so that's all I wanted to cover in this revision, this example. So you can work through the example that we introduced in that revision exercise. You can work through in revision A. There's a different problem that was introduced there. That's the same. So this is that's revision B. Revision A. Where are you? Anyway, go into revision A, and there's another problem that you can work through. Yeah, this one. So you can work through this problem as well in the same way. Okay, so if there are any questions about the course or any other things you want me to go through, please drop me a line, and if there are enough people with the same question, then we can set up another Zoom session and so on. And that's pretty much it for the course, right? Best of luck with the exam, and see you soon.